Hello, my name is William Kirtu, and I'm just going to do a quick demo of my final project for CSC 578. Alright, so the objective of this project was given a historical data of climate conditions from 2009 to 2016. We're going to try and predict the temperature of the next hour based on climate conditions and temperatures, so the features, over the last 24 hours using recurrent neural networks. So here I have my imports. So do that real quick. So we're using pandas to import our data. We'll be needing NumPy later. Matplot for plots, and obviously Keras to actually run these models. And the next thing we're going to do is read in the training data. So in the training data, we have 52,566 rows of data with 14 columns, or our features. So we're going to import that right now. So as you can see, our index column is just the date and time. So for example, January 1st, 2009 at 1 a.m. And these are the features. And for our target variable, we are looking at the temperature, degrees Celsius. Similarly, for the test data, we're going to import that. And for the test data, it's already in Keras ready format. So each row consists of a sequence of 24 days, and those will be used to predict the temperature in the 25th day. All right, so that's imported. There's a little bit of EDA here. This just gives us the data types for our features, which is just all float values, so it's pretty easy to work with. Similarly with describe, we get, the mean, min-max values, the quartile ranges, etc. We can also see the correlation between the features here. And you can see for our target variable, degrees Celsius, it's got a high positive correlation with Kelvin, which makes sense since it's just a different unit. And the temperature of the dew, similarly, another high correlation. VP max, what else? Rho, all these things. It has a high correlation with a lot of variables here, except for the last three, it appears. And we can get actually a better look at that. We get better visualization here by plotting it. So these are all our features plotted over time. So so these are all across all the days in order. The second one here, the temperature degrees Celsius, is our target variable, so we can see how it relates to others, like visually. A lot of these other features like teapot, tdew, vpact, they all have a similar shape to the graph. Rho looks just opposite of what it looks like. So I guess this first feature and the last three I don't really see any similarity between them, like visually, but I'm sure they have impact, so we'll see later. So now we have to normalize the data. Here I'm just applying a z-score function to the training and test data. I'm going to separate out the target variable from the training data. Well, not separate, but I'm just going to make it its own thing. Y-train, so that's the shape right there. And now we're going to make the training data Keras ready by doing some series of concatenations. So it basically has the same formats as the test data right now. And we can see the shape to make sure. Yep, 52,542 and 336 columns as specified in the homework documentation. And then this is the shape of the test document. Now we're going to convert the training and test data to 3D format for Keras. So we just do that right now. We see the shape. So we have, for the training, we have the 52,542, 24 time steps across the 14 features. And now we're going to train the model. So network type is just which network we want to use. So I have it set up so if you type in 0, you're looking at single layer, 1 is multiple layers, 2 is bidirectional LSTMs, and 3 is when we implement convolutional neural networks. So right now I'm just going to run it for network equals 0, so it's basic single layer, and it's actually stateful right now the way I have it set up because that was my optimal model. So while it's running, I'm actually going to pause this and then continue. This is the output of the training. So you can see we trained across 50 epochs, and you can see the how many seconds per step, which is pretty low because of the stateful LSTM, as well as the loss values. And we actually get the a visualization of it. So these are loss value, training loss values across successive epochs. You can save the model, which I already done, and load a different model if we need to. And I have a bunch of them saved actually. As for model evaluation, for non-stateful recurrent neural networks, we're just going to use model.predict on the test set and return the predictions. Otherwise, if we implement statefulness, which requires using batch size, this won't work. So we have to, the way I've implemented it is I'm going to use different batch sizes for the train and test set. So I actually create a new model with the same parameters, but for the test set, and I'm using a batch size of 1, so stochastic. And then I'm going to copy the weights from the old model, so the model we've trained already, to this model, and compile it, and do a new model.predict on the test set with batch size equals 1. So this is one way that I found that I could get statefulness to work. It took me a while to figure this out, but there was a reference I used that helped a lot. And then I invert the scaling, which is these values were, oops, let's make sure I actually do the predictions here. So I'm going to let that run. I do some denormalization here once that was done running. Those are the values I get, which are definitely different from what I got with my final model, from what I can see. And then we can actually plot the actual versus predicted values here, so we can actually visualize it. And then finally, we just write the predictions to the CSV file here. If I could have done more, I probably would have looked at the pre-processing more, see if, removing features or creating more would have improved the model. But that's all I have for you for now. Thank you so much for your time and enjoy the rest of your summer.